now the government of China pays for people to go. I don't know what they stipulate, and Korea does too. But you're paid. You're paid if you have a really high GPA, you apply for fellowships. And all of my American graduate students, I think but one, was on, I think, I'm not sure if the other one wasn't, were on fellowships. They're National Science Foundation fellowships, NSF. Hear me now. DOD, Department of Defense, there's a SMART fellowship. Those are the ones I'd recommend, and NSF, DOD, and DOE, but more so DOD and the National Science Foundation. There's also Air Force, AFOSR fellowships. There is NASA fellowships, and I've had people on all these. They pay at a rate 30 to 40,000 a year plus tuition. Now, and there's all sorts of waivers. You don't have to start paying your student loan back until you're out of grad school too. Because I had student loans. I didn't have to pay anything until I was done with grad school. Grad school was paid for. I hope you understand what I'm trying to do here. Now, your overall, I want to say, enjoyment of life, for lack of a better term, goes up with more education in general. You can't be too educated, but I've never found anybody that had an advanced degree in either the sciences like chemistry or something like that, or pure mathematics, or engineering, or for that matter, law, or medicine, like a medical doctor, that ever regretted it. There might be one person that passed that got a degree in art history, that it just wasn't worth the cost. Now, I'm just saying that as a courtesy. You did very good class. You got very bright people here. You'll never regret that opportunity, and it usually, the longer you wait, the harder it is. So my recommendation is get the last degree you're ever going to get sequentially, because you need all that knowledge a lot of times for the other courses you're taking. Just remember what I'm saying. The other thing I'd tell you to do, especially co-op people, spend some time reading like the latest technology. Look at IEEE Spectrum. It's a good place, but you can look there. You can look at Scientific American, these broad brush journals that take a look at the emerging technologies with the most promise. There may be something that you're very interested in. Get in while it's early, when it just emerges. Think about this. If you knew what the internet commerce activity could be back in 1991, 92, just at the beginnings when Google and all these things sort of came in, if you would have jumped on that trend, you'd be down on some beach in the Caribbean probably for the rest of your life after a couple of years, if you wanted to be. There's so much you can do. Now, people, right now, there's a couple of things that are very interesting. I don't know if you know this, but everything's going to really drones. They're going to unmanned aerial vehicles, unmanned automobiles. They're going to have all sorts of delivery options. There's all sorts of technologies around that to miniaturize, to more or less take things and put them all, integrate them all into one. And there's embedded system engineering. There's everything like that. The terms mean very little other than they want to make them smaller, faster, and they want to take any legacy technologies and make them digital. And then the people that develop the interface for that, my wife's one of them, they get paid a good chunk of money. And all that stuff is very important. There'll be things where they're going to take, one of the things I'm interested in is radar. Well, in radar is kind of a very computationally intensive thing. It takes memory, it takes a lot of electronics, it takes power source. The thing about it is with radar, on the frequencies we transmit, you can easily bury a communication signal. So if you want to broadcast your position to other people, you can bury it within the radar signal. And they can extract it and they can communicate back to you. That means you have one platform transmitter to do two things. Before, you never did that. You'd have a separate comm link, you'd have a separate radar. They want things like adaptive radar and also that use machine learning algorithms. That's just making computers think like you and teaching. That's all it is. It's called neural nets. And it's amazing what they can do. You know, Google has a lot of money. And there's sort of a state-of-the-art program in chess called Stockfish. Does anybody here know anything about Stockfish? Anybody here ever play chess? If you've played chess, you know something about it. It's a complicated game. And to look more than a couple moves ahead takes some doing. But anyway, Stockfish is sort of state-of-the-art. It's not a neural net. It is something that's just a computational program that evaluates the strength of positions and looks further and further down. It's called the depth, how many moves in advance. And the next move it makes, it will be the move that helps its overall strength of position go up. Now I'm not going to get into all, but it's not a neural net. It's not artificial intelligence. And it's a strong program, don't get me wrong, on a very strong processors. I mean, if you have them parallel 4, 8, 10, very fast processors, it's incredible. But Google took it to the next limit, and what they did was develop an artificial intelligence, a machine learning type of computer program to play chess. And that thing basically is destroying this and any other standard computer programs because it's learning as it's going, just like you learn. It's called neural networks. And it learns from all the past games. So it's looking at all the past games recorded. And it's almost impossible to get a new move set on this thing. It already knows what to do. So at best you get a drop. And the first time it played Stockfish, it didn't lose any games. And it won a whole bunch against this computer that was thought unbeatable. Now, give you an idea of this. Grandmasters can't touch Stockfish. The strongest is Magnus Carlsen right now, world champion. So this is what artificial intelligence can do to something silly like chess. What it can do to things like designing networks, instead of using your brain, let it think after you put in the parameters, and it learns as it does these designs, is incredible. So I'd encourage you to think about at least having part of your advanced education into something related to neural nets, all right? Something related to machine learning. You're going to hear all about this. Some of you will be working with that area directly applied to something. I've done genetic algorithms and all these things, optimization algorithms, to do things like design antennas. That's not a true neural net. It's something that's using a weakly it's called a weak probabilistic type of approach to design antennas. And I don't want to get into all of it, but it's fairly advanced, and it designs things that no human would figure out on its own. This takes it to the next level, and that's the world you're living in. And I can think of a whole lot of things that would be of interest. For instance, just predicting the stock market with neural nets. Surely there's people out there doing that. Sure, but I hate to say this, and I mean this in a sincerely humble way. People involved in high finance oftentimes are very weak mathematically with technology. I had a kid graduate out of here, good student, strong, 3.8, 3.9. And he got grabbed by these people on Wall Street for a big salary. And he called me up like 5 or 6 years later. He wanted to go to grad school. So I said, well, what are you doing? They're not making enough money. Oh, I make more money than I can ever use. I hate this place. They don't know how to do a lot of things that I knew how to do. They're not good programming. They're not that great with math. That's kind of an oddity. But that's another area, finance. But really, it's for anything, medicine. Think of something you're interested in, look at neural nets. The other thing I'm going to tell you about that I hear all the time is quantum computing. Have you heard about that? True quantum computing the only way you can do it has two things, usually photons that I know of, and they're, quote, entangled. Now, entangled means the properties are inseparable, one from the other. And when a state of one changes, automatically the other one changes no matter how far apart they are. And it changes instantly. It seems to violate the speed of light. but it's not energy, it's information. And that can travel faster than the speed of light. I don't want to go there now. I'm just going to tell you this kind of stuff can happen. It irritates me. It irritates a lot of scientists. So what they do is have entangled particles that have probabilities of certain states. And I don't like this. I'm just going to tell you this because this sounds like pseudoscience. But, I mean, the reason I say I don't really argue with it is because the bottom line is the evidence. What evidence do you have for that? And the fact is they can do a computation. But these particles disintegrate down and they become uncoupled in like nanoseconds or picoseconds. That poses a problem. Unless you get down to cryo temperatures, which is liquid hydrogen, or really liquid helium, pardon. It's absolute zero kind of depth. That's hard to get. It's very expensive to hold the thing. However, that said, and I'm telling you this now because this is a smart class. I'm not going to tell some of the classes of the past and another class I have this, but this is something that is of interest. So the biggest thing they've done, unless something's happened I'm not aware of, with real quantum computing, they use this as a buzzword, it's not quantum, is the ability to factor the number 15. I may have said this before. The number 15 is 5 and 3, 1 in 15. All right, that's the biggest real problem they solve with true quantum computing, which tells me, and they say the real problem is something called coherence. Really, these particles, any tink in temperature just it shatters everything that you want to do. I won't even get into how you do quantum computing because I'm not there. I don't live in that world, but I've talked to people that are. And so when they use the word quantum computing, it usually means something not quite that, because that's what real quantum computing requires: entanglement of particles, and it requires the ability to have these particles, say you got 100 of them, actually interact in a way so that you can check them later. As soon as you check them, you pull them out of that state of entanglement. And if these particles change state in a certain way, it'll cause these particles to change in a certain way, and you can make a decision based on that. Now, that's not really a good explanation to you, but it gives you an idea about how this crap works. And I don't pretend to mess with this very often. I just read about it. That's a hot area. You should at least become familiar with it and what the truth is. One last thing that they're talking about is really all this nanoscale engineering and really making things so small. And when I say nano, we're talking 10 to the minus 9th meters feature size. It's insanely small. This is getting subcellular size. Do you follow me on this? It's so small. But they're going to have stuff, and they're called nanobots, robots that they can put in your bloodstream, and they can be programmed to selectively go and like destroy cancer or something like that. But they have many other purposes. So consider becoming aware of, and there may be other technologies I'm not aware of. I mean, in medicine, I know there are. They're looking at extending life forever. Basically, when you die, a jellyfish never has a natural death in terms of it doesn't age and just become decrepit. Something eats it or kills it. So jellyfish have like the secret to long in your DNA and everything. If there weren't certain things programmed in it, you'd live forever, but you're programmed to die. That's the bad. And you basically wouldn't age. Maybe that'd be a better word. So anyway, they're working on that. And if you get into anything related to health-related, life extension, disease elimination, that's another hot area. How electrical and computer engineering directly impacts that is kind of a stretch, but it does. So consider that. Now, back to the real world. And I hope you don't mind me telling you that. But I want to do this, and I don't want to do it the last day of class, where everybody's basically, what's on the phone? So, questions before you go. I gave you a bunch, right? Did y'all have any questions? Didn't you ask me about a figure?
Yeah, it was for the S parameters though. Your textbook is different.
It's a different. I noticed you have blue blue figure outlines when I had red or orange. So this is an older book, but I can get a newer one, and I will next time, and I appreciate that. Did you have a question about any S parameters? You're kidding, for real? You winced, Isaac, no? Well, we're gonna do one. You wanna pick it or you want me to? All right. Let me warn you about S parameters. The real trick is realizing you're on a transmission line, and there is a transmission and a reflection coefficient that affects everything. So I'm gonna go through and give you a typical one. Matter of fact, in the book, I'll try to mirror something in the book first, and then I want to go through something else. I'm just thinking about when I was a student, we're sitting where you're at. 76, 77. I'm trying to think of what's coming out. So VLSI technology just is coming in and to a different level. And computers coming in, calculators are now becoming available to everybody, and they're cheap. But we still had LED, not LCD displays. And there was no internet. If I knew that an internet was going to happen, I'd be flying around in jets, probably not having a worry in the world. But I mean, things like that happened in my lifetime. Stuff that is so bizarre and fast, it's unreal. Things are increasing at an ever increasing rate. So by the time you're my age, who knows? Maybe you'll be living on Mars. I don't know. Anything's possible these days. They've got stuff. You know, the Japanese in the 80s wrote this stuff, and they were going to do it, to do asteroid mining. I thought, what in the world? Because of these rare earth elements that they need for the aircraft industry and all that. There's a lot of gold out there. That's coming back into vogue. And you'll notice all these billionaires that want to fly up into space. Thinking, why they want to? You gotta wear a diaper. I mean, the last thing I want to do is get out of, where I am confined and basically in an environment that can kill me if I have any problem. But they do. Well, I think there's a method to their madness. I think there's a lot more money behind this than we think, and they're not stupid. They didn't get where they're at being stupid. So when they say space, the final frontier, if you ever hear that, you may find out it is. And anyway, back to this. What I'm going to do, since we're talking about S parameters, and I think a lot of this, you're not vested in this, as I said, it wouldn't be on the quiz, but I think I might put it on the quiz. No, just trying to get you to be a 10. If I'd say something like that in certain classes years ago, I'd have hysteria. It's a joke. It's a joke. I'm not kidding about this. One time I just decided, all right, the person that I call on that answers, they can call in the next person for the next answer. Holy crap, I almost had a fist fight. I'm not crazy about this, but we'll do this one on, it's example 10.6. And you tell me if I'm wrong. But you got a transmission line with a characteristic impedance of 50 ohms. And then he has, you gotta make sure it's where the L goes. Then he has 25 into 50. And then this is connected
to another transmission line with a characteristic impedance. Draw this a little better. Of 50 ohms. So this is the thing I want the S parameters of right here. Y'all follow me? Now, you look suspicious. Is there something wrong on this thing? Now, remember, you gotta label your ports for starters. This is port 1, port 2. And here on port 1, we have an incoming signal V1 plus, and we have an outgoing signal V1 minus. Here we have an incoming signal V2 plus and an outgoing signal V2 minus, right? Just to be clear. When you take a look at the relationships, V1 minus is equal to S11 V1 plus S12 V2 plus, and V2 minus is equal to S21 V1 plus S22 V2 plus. That's the standard statement for a two-port. I didn't put it in terms of a block matrix, I'm just stating it explicitly. Now, after that, we're going to go ahead and evaluate each one of these things. And I'm going to warn you, there can be tons of mistakes made here, simple ones. And here I kept the transmission, the impedances, characteristic impedances the same. That doesn't have to be the case. You can take 75 ohm cable like Charter cable or Spectrum cable, come into something and break out to 50 ohm for the inner part of the house. So just remember, it doesn't have to be the same on both sides. So when we're doing this, we start with S11. S11 is really equal to V1 minus over V1 plus, assuming V2 plus is equal to 0. And what that breaks down is simply, and you can put this down explicitly, it's simply the reflection coefficient at port 1 and then put port 2 matched. What it means is this transmission line here is terminated into Z0 in this right here. So nothing is reflected back. There is no V2 plus. Do y'all follow me on this? Okay. It's simply the reflection coefficient. Let's look here and just calculate it ourselves. If I want the reflection coefficient at this port, please be with me on this, stay with me. I want the reflection coefficient at port 1. Well, this is a standard transmission line. Now, watch me on this. Really, I want the impedance I'm going into, right? And I'll call this Z in port 1. Z in 1. Minus the impedance I came from over Z in 1 plus the impedance I came from. Isn't that the definition of reflection coefficient? Always the impedance you're going into minus the impedance you came from over the sum of the two, correct? All right, what is the impedance I'm going into looking here? Now, make sure you see this. Trust me on this one, people mess this up all the time. They get casual. I've got 50 in parallel with 50, don't I? Y'all see that? Mm-hmm. This is 50 in parallel with 50, not 100. Even though it's 50 ohm, this is a transmission line, many wavelengths long. Think of it that way. So it's 50 in parallel with 50, that's 25, right? 25 in series with 25 is 50, correct? So this is really reflection coefficient is 50 minus 50 over 50 plus 50, or it is 0. Got it? That means over here, S11 is there. So we got one of the four. Y'all with me? Now, the next one I'm going to do, because I like to do these things, we do reflection coefficients, do them all. When you do voltage gains, do the forward and reverse at the same time. So here I'm going to get the reflection coefficient here at this point. So what I'm looking at is Zn2 I need right there. And this would be S22. And that's equal to the reflection coefficient at port 2. And it's really V2 minus over V2 plus, assuming V1 plus is 0. So really port 1 is matched now, not port 2. Do y'all follow me? It's just terminated into 50 ohms. So it's a 50 ohm port there. And when I do this, I have S22 equal to reflection coefficient. And that's the impedance I'm going into. I'm going to erase this. So that's equal to the impedance I'm going into, Zn2, minus the impedance I came from over the sum. All right. So one of the things you guys are saying is, I got to make sure I get this right? All right, follow me on this. When I look in here, I have 50 ohms in parallel with 25 and 50 or 75 going. Make sure you get that. So that means when I have the actual input impedance to port 2 is going to be 20, it's 50 in parallel with 75. So that's really 1. That's going to be 1 over 50 plus 1 over 75 if I want to do it that way. And $30 ohms, is that right? 30 ohms. So that means I have 30 minus 50 over 30 plus 50 or 80. And that means I have minus 20 over 80 or minus 1/4. You agree with that? All right, we got 2 of the 4. Now over here, and I'm going to do it here, I'm going to go ahead and get S21 and S12. When I look at S21, that's V2 or V2 minus over V1 plus, assuming V2 plus is equal to 0, right? It's the forward voltage gain. Please keep that in your mind. It's the forward voltage gain. Well, how do I get that? This is important. What I want to do is think like this. When I have a V1 plus, and it's propagating in here, the value of V1 here is not felt here. You hear me? And here's why. This is a transmission line, but here is where we have a reflection coefficient. We just calculated, right? Now, I mean, it could be. I tell you the truth, I think the reflection coefficient of S11 is 0, so in fact it is. But if there's a reflection coefficient, there's a transmission coefficient. 1 plus transmission coefficient times this is the actual voltage right here. Y'all follow me in that? Now, does not have to be the same. In this case, it is. This happens to be V1 plus. We're going to see for the reverse gain, it's not. Now, once we have this, we want the ratio of the output voltage. So whatever voltage here is developed, we just need to find the voltage here that's developed. You all follow me? And this is simple voltage division. Now, follow me on this. I want to make sure you see it. I've got V1 plus right here, correct? Mm-hmm. That voltage is developed through the series combination of this and 50 in parallel with 50 or 25, isn't it? Do you see it? So it's like we have 25 ohms in parallel with 25. And here's my output, plus the minus V out right there, and this is V in. So I can see it's just going to be 1/2. Do y'all see that? The output voltage will be 1/2 the input. Do y'all follow me? That means here, S21 is 1/2. And I didn't have to worry about this right here because that was 0. The transmission coefficient was 1 because the reflection was 0. Correct, class? Now I go over here, and now I'm going to calculate the actual S12. So S12 is equal to V1 minus over V2 plus, assuming that V1 plus is 0. So V1 port is matched, in other words. Y'all with me on that? Okay. Now here, we're going to see something. This is going to make things a little different. So I'm going to erase this. That's port 2. All this yawning is getting me ready to yawn. Here I have V2 plus coming in, all right? Now, we have a reflection coefficient on this port that was equal to what, minus 1/4? No, sorry. That's S2. Yeah, that's it. All right, so the reflection coefficient is equal to minus 1/4, which means the transmission coefficient is equal to 1 plus the actual reflection coefficient, and that's 3/4. You see that? Right? Just make sure you're convinced. So that's transmission. It means this voltage developed here, V2 plus, is not the same as the voltage here. This is in a transmission line. And remember, right at this intersection, some of the signal bounces back and some of it goes forward. And the amount that's going to go in this direction, I call that forward, we call V2 prime. And V2 prime is actually equal to the transmission coefficient right here at 2, pardon me, times V2 plus. Y'all with me? That transmission coefficient is 3/4. So this voltage here is only 3/4 the voltage here that was incident. And it's real important to see that. Because a lot of times people just say, oh, it's the same as that. No. This is a junction where there's an impedance discontinuity and we get reflection. Now, of that voltage here, some of it is going to be developed on the output, and we can do that by simple voltage division, all right? But we have to, we've got this parallel resistor, but it really doesn't matter because the voltage is really developed across the entire voltage, V2 prime, and the series combination of these two. So what I'm gonna do, and I'll do it right here. If you look at this series combination, I have 25 ohms, and then I have 50 ohms. And this is my output voltage. Remember, the flow of the signal is this way now. Here's my input, V2 prime. Y'all see that? Right, the signal's going that way. This is literally my input, isn't it, class? I want to know how much of this is developed here. Well, it's going to be 50 over 50 plus 25 times V2 prime, right? Jacob, you're looking at me like I'm lying.
Where did the parallel 50?
Parallel 50 doesn't matter because see how this voltage is right across there? I don't care about this thing at all. What I need to know is how much voltage is right there on the output port. And a good question people have is, well, Dr. Baginski, how come you didn't take a transmission coefficient going there, right? I mean, doesn't that seem logical? You don't need that for that case. I'm trying to say this in a way that's going to be meaningful. Because the only thing I need is the voltage developed here at that port. It's still not right. If you look in the book, I don't know if he has a detailed explanation, but the voltage here on the output right here is the port voltage. Does that make sense to you? It is the port, like when I got the voltage right inside here, it wasn't the voltage in the transmission line. You see that? The voltage I want is the voltage here and the ratio of this voltage to this voltage right here. I hope that makes sense. It's not exactly doing justice to this.
Right, so where did you get the 50 on?
Here?
No, but you said that you have it to the left right here, the one.
Here, because this is a 50 ohm port that's connected to. See, this characteristic impedance over here is 50. Maybe we should have used different values, but you see it? All right. So that means V2 or V1 minus over V2 plus, assuming that port 1 is matched, will be equal to really 3/4. Actually, let me do it this way. When I look at V1 minus is going to be equal to 3/4 V2 plus times the voltage division, which is going to be 50 over 50 plus 25. And that means I have 3/4 times, and this will be 2/3. And then that will be V2 plus. That's V1 minus. And then if we divide by V2 plus, I get this, and that's equal to simply 1/2, right? You agree with that? And if you look in a book, I think he has this. So that means my S parameters here are going to be S11, which is 0, right? And then S22 down here, which is minus 1/4. And then I have S21, which is, is it 1/2? 1/2. And S12, which is 1/2. And that should be in his book, but I can't tell you. Let me try to do a little more justice to this port business. So you're thinking that there should be a transmission parameter there, right? The real reason there isn't, this is not a transmission line. This is just a resistive network. Anytime we're worried about a voltage jumping from here to there, we have to include the actual transmission coefficient. Because this is transmission line, non-transmission line. I hope that helps. I don't feel a lot of, sometimes it's hard to satisfy. When I'm thinking in my head, how do I explain that? I don't have a really good way other than to tell you the resistive networks don't have that problem. Okay, so that's that problem. Did you look at any of these things with resistors? I mean, with the inductors or capacitors or not? If you didn't, I want to just mention something.
With the S-parameters?
Well, there are a couple of them in there. I gave you from home. You're going to need to know that. But I want to do one quick one, and here's one. Because then all those S parameters, they become complex. Magnitude at angle, real or imaginary part. And that gets a little more tedious. So I'm going to just do one little thing, and then you get your quiz. You'll be on the board. Can anybody tell me if it's going to rain? And then tell me how hard.
Yeah.
Huh?
Mine says-
I mean, if you look on, you got web app. Don't you have weather apps on your phones?
mine says
128%.
120.
It's really going there.
We're really,
128 a ton.
it's 204.
All right, well, it passed. I had to decide on that.
I use AccuWeather. It's generally speaking more correct, but now you got me. While you're doing that, I'm very curious. You know why? Because I have to go up. And so you,
It says it's raining now. Yeah, 128% chance. It's just
that's
that,
not the usual rain. We usually have
Yeah.
rains and pours rain.
It's like,
I mean, I can see under the door and it doesn't look like it's raining out there, I'll be honest with you.
you can probably that's a fantastic talent. You can tell the
I mean, yeah, normally when it is, I see the water right through the door.
Auburn is way too
There's about a half-inch gap
If
underneath
you look the other
it.
way, it's probably raining.
Yes, he says 6 o'clock. It's, 35% chance at 6.
Let me tell you something about this time of year. Right? Like, I make no secret of the fact I like to go fishing. I like my boat. There's a problem getting out of the boat in the water. All right, lightning, especially when you're 10 miles away from where you're putting in your trailers. And here's the problem. At Lake Martin, it can say 20% chance of rain, which is about as low as it gets in the afternoon in Alabama. And I can get out there where I'm fishing, and it's getting a little cloudy, but it's Alabama. And then I hear this distant, and I look, and I see it's probably raining. And then as the thunder gets closer and closer to the lightning, now I've got to make a decision. Do I want to kill myself going that way or beach the boat and head for cover? I'll tell you some crazy stuff happened. I had a friend of mine who was a student here. He's a maniac fisherman, bass fishing, fishing tournaments, fishing out there. This is with monofilament line, I think, before. Casts it out, the line's not sinking in the water. Boy, that's strange. Then he starts feeling the hair in his head get up. Now, I failed to mention it was raining and there was some thunder and lightning. But of course, he was catching fish, so it can't be a problem. And he realized, because he was an electrical engineering student, a pretty good one, sounds like there's a charge being developed on my head. That means I could be a strike point for lightning. And he flew into shore, beached his boat, ran for cover under some of these large, you happened to be in an area where they had done some cabling, and they had these large empty spools, you've probably seen them, where the wire's off it, and they're basically a cord, it's like a table, and these are huge ones, so this is for some big one. So he got under there, and he said it became a war around him. Lightning was hitting all around him and stuff like that. He could have been killed on that water. So if you ever feel the hair standing up or the hair in your head, get out of that area faster than you can imagine. You may save your very life. And I'm serious. So here's a simple one, and it's like this. I have an inductor. The inductor has an impedance of J 50 ohms. I'm just showing you this for one complex thing. I'm going to have a characteristic impedance Z naught of 100 ohms here, and I'm going to have a characteristic impedance of Z naught equal 100 ohms here. And I want the S parameters here. So I put the value in for the impedance. I didn't give you a value of L. I just said it's J50. So if I want this one, anybody now, what is S11? Can anybody do that? Nobody? Well, what is it normally? Isn't that defined as just the reflection coefficient of port 1? Right? Assuming port 2 is matched, correct?
Yeah.
All right. So now that we got that far, this is always what? Zn minus Z naught over Zn plus Z naught, right?
Mhm.
Now, what is Zn? This is port 1, port 2. Say that again.
J50 plus 100.
Exactly. So it's going to be 50, J50, or I'm going to put 100 plus J50. All right. What's Z naught? Minus 100 over 100 plus J50 plus 100, right? So really that's J50 over 200 plus J50, correct? So it's really, if we divide by 50, J over 4 plus J. Okay? Just getting rid of this stuff I don't need. And if you want to, you can do it this way. You can go ahead and just take this and make that one at an angle of 90 degrees. Then take the magnitude of this an angle, and then just do the math. But here it's going to be complex. Can you see that S22 is going to be the same by looking? S22 is the reflection coefficient at port 2, and that will be equal to S11, right? You'll notice it's complex. What about S21, the forward voltage gain? What's that equal to? Well, think about it. For doing that, I need this transmission coefficient, right? If I want V2 minus, that's how much gets out from something coming in. So now I'm just going to put this down. That's the transmission coefficient at port 1, right? Once I have that, now I have the voltage here, then I have to get the voltage division between here and here, right? And that voltage division would be 100 over 100 plus J50, correct?
Mm.
Y'all agree with that? All right, that's complex, right? Because this is equal to 1 plus reflection coefficient, right? At port 1. Just remember this. Now, these complex numbers sound like they're no big deal, but trust me, they're a big deal when you're doing them on a calculator, on a test, or a quiz, because people fumble that up all the time. I'm just trying to make sure you know. All right, now for your quiz. Do you have a question on this before I take off on the next one?
Could you just do this one too real quick?
Sure. S21. Oh, you want S12?
Right.
It's the same as S21 because you see how that network's symmetric?
Right.
And here's the way you tell a network symmetric. You look at it this way, inductor really into the impedance. If you look at it this way, inductor into impedance, that means S21 is S12. and S22 is S11, and those are the kind you love. But a lot of them aren't symmetric, and that's where you have a forward gain caused by a transistor. Remember that. Or by so now your quiz. Please do me a favor, spread out. Put at least the desk or two, yeah.
Do we need to start?
Yeah,